Well, here we are. We're going to do a complete FRQ, all three of the long questions and four of the small ones, and we'll take them one at a time. But before we start, we should go over this, because going for the exam, there are certain things that you really can't have, and you should know about those. Some of them are pretty easy to figure out, like you can't bring your own periodic table. No. You're going to have to use theirs. Forget about bringing anything that's got a periodic table on it, including clothing or whatever. Also interesting, you can't bring any highlighters. Forget that, unfortunately. And certainly you can't have any extra reference books. So, nope. So you're going to have to take your potions books and leave them back at home. Protractors in AP Chem are a no-no, and so are little rulers. And you know, for multiple choice, they're not going to let you use a dice. No. Liquid paper even is a no-no. And surprisingly, water you can end up having. So no water and no snacks. So you're going to have to leave your mackerel and marmite at home and not use them on the AP exam. So, also I'm pretty sure they have a miscellaneous category that says you can't have any moles or little pets with you. Now, they have a complete list of things that you can bring, and just go to the link. It says what you can bring and what you can't bring, all the things that you have to have for the exam. But one of the things that you really need, especially for the FRQ, are a couple of pens. Now, you can use pencils, but they say you really should be using pens which are nice and dark. But if you insist on pencils, make sure you use dark markings. And also, you can't use mechanical pencils. They're not allowed. You are allowed to bring, of course, in fact, if you don't bring one, they'll wonder what's wrong. In fact, you'll have to sign a waiver. You're going to have to bring a calculator along, make sure it's charged up. And if you want, you can even bring a backup calculator. So here's my calculator ready for the exam. I've got that there. And you can have a timer with you, a watch, but the watch can't have any alarms. It's got to be a totally dumb watch. You can't have any internet connection with it at all. So if you're going to bring a watch, make sure it is a old school watch. I have some old school ones here. I've got my non-internet connected. I'm going to use an hourglass, and I've got the long questions are about 20 minutes each, so I got a 15-minute timer, and I've got a 5-minute timer that I'm going to use to sort of time myself for the question. Probably your school is going to record. Here's our FRQ, and I've got my 2 pens, I've got my timers, I've got my calculator. Let's see if I can do question number 1 in 22 minutes or less. I'll get my 15-minute timer going first, and then I'll have my 5-minute one when that's used up. Okay, pen, calculator, ready to roll. Let's see what they got here for us. They've got, you know, their standard readings for show your work and receive credit for your answers, pay attention to sig figs, all the rest of that jazz. Nothing new here. And they say 23, 22 minutes. Okay, let's see. We start our timer. I better get going. Here we have ethanol combusts in air according to the equation above. Ethanol, notice we got a liquid here. Careful with that. Gas, gas, gas. And it's an exothermic reaction. Is the O2 oxidized in the reaction, or is it reduced and justify in terms of, oxidation numbers? Well, let's see. Here's the oxygen in ethanol. Oh, wait a second. No, the oxygen here, gas that we're dealing with. O2, well, as an element, it's got an oxidation number of 0. Now, a reader would end up saying, okay, that 0 up there indicates the oxidation number of oxygen as a reactant. Now, let's see here. We have it as CO2, and now we know in a compound, unless it's a peroxide, oxygen has a oxidation number of -2. Let's check here in the water. Yeah, hydrogen is +1. This is 2. This isn't a peroxide. So we've got 2 oxygen atoms with a charge of -2, which means they're going to have to pick up 4 electrons. And I've shown my oxidation numbers. And, I make sure I have to answer the question. Is it oxidized or is it reduced? Well, we're going from 0 to -2. This is reduced. I can say gained electrons, and that's all I need. Gained electrons, period. That's taken care of. Good. We got a point. That's an easy one. Sample of ethanol was combusted, and the volume of CO2 gas produced was 18 liters. Okay, we're getting a gas, and in liters. Measured at 21.7 degrees Celsius at 103 atmospheres. That's what the gas was at. Determine the number of moles. Oh, PV equals nRT. No, we're always going to use the PV equals nRT on this thing. But I'm going to write it this way, the easy way. Moles is going to be equal to pressure times volume over root, or RT. Now let's make sure we get everything right. We've got pressure. It's in atmospheres. Perfect. If it was in torr, we'd have to change it to atmospheres. So we got 1.03 atm. And then volume is 18 liters. Okay. Now this is pretty close to room temperature, 21 degrees, 1 atmosphere pressure. I know the standard temperature and pressure is at 0, and we get 22.4 liters makes 1 mole. So this is going to be close to that. So this is going to be a little bit less than a mole for my answer. We'll have to double check that later. And now we're going to divide by, okay, now we've got an equation sheet. We'd flip forward to it if you didn't remember what the gas constant R was. But really, this is one we use so often, and you know you're going to use it. So it's worth not having to flip forward or go into your little orange booklet that they have. This 0.08206. Here we go. Don't even need that fourth. Sig dig. Atmospheres and liters per mole Kelvin. I'm supposed to set a good example, but I know everything is in atmospheres and liters and Kelvin, so the units aren't all that critical. And then we have our temperature, and don't use Celsius. Please don't use Celsius. 21.7 plus 273. It should be 273.15, but 273 is going to be good enough for this answer, and that'll be kelvins. Our kelvins cancels. We end up getting moles. We just have to do this on the calculator. Oh, by the way, one common error, and you're probably past that by now, is on the equation sheet, the first gas constant given is the energy gas constant. We only use that when we're dealing with energy, joules, delta G, or voltage. Use the 0.08206. The torr one is hardly anybody ever uses, so I wouldn't bother with that. So calculator time. Like I said, I figure a little bit less than a mole because 22.4 liters is a typical STP thing. So let me clear, and we've got my calculator, and okay, 1.03. Okay, got that number right. Times 18. Don't need to put the 0.0 down. Divided by 0.08206. Yep. And then, of course, we've got our Celsius to Kelvin conversion, but it's in the denominator. And my order of operations for this calculator is you divide by everything in the denominator, or use a heck of a lot of parentheses, but 21.7 plus 273. I'm not going to bother with the 0.15. Close parentheses and see what we end up getting. A little bit less than a mole. Yep. I would say this is going to be 0.767 moles of, if you want to be really, really nice, CO2. It makes sense. And 3 sig is going to be fine for this. All right. Found the number of moles of CO2. Now, this would be in a booklet, and you'd be flipping back and forth on this. So you could see your previous answer, 0.767, when you go on to this next page. See, determine the volume of, now notice, this is liquid in mLs. We're not dealing with a gas anymore. We're dealing with a liquid that was combusted to produce the volume of CO2 collected in part B. And they give us a density. Okay, so they're going to toss in a little bit of density here. But let's first find out how much ethanol we had to use. Now, this is where you would see both pages simultaneously. exam. So I'm going to pull my previous answer out, and we know we had CO2. We had 0.767 moles of carbon dioxide. That identifies it. That keeps things so I know what's there. If you had a different answer than this, you'd put this down and you would be double penalized. Let's say you put down 0.677. You got some numbers mixed around. As long as you're consistent with your answer, you're going to be fine. Now, I'm looking at my reaction, and here's the CO2, 2 moles. Here's the 1 for the ethanol. So we know there's a 2 to 1. This is just a simple stoichiometry thing. So I'm going to multiply by my 2 CO2s and 1, I'll just write down F. So I don't have to write the entire formula down. That's going to give me moles of ethanol. Now I'm going to have to figure out the formula weight to get grams, because eventually we're going to have to use density to get to milliliters. So, moles to grams is pretty easy. Methanol, we had C2H5OH. That carbon is 12 times 2. We've got 6 hydrogens, so it's 1 times 6. And then we've got an oxygen, which is 16. Really, you should have those memorized. And they're all pretty easy ones to go through. And let me add this up. Let's do a little calculation here. 12 times 2 plus 6 plus 16. Okay, 46 grams per mole. So, all right, 46 grams per mole. This can be close enough because we've only got 2 sig digs for our density. That's not going to be any big deal. So 46 grams per mole. And let me do the calculation right now, just together. I've got my 46 in my calculator already, and I'm going to multiply times the moles of 0.767. And don't forget to divide by 2, because you only need 1 mole of ethanol to get 2 CO2s. This gives us 17.6 grams of ethanol. This is our liquid ethanol, and that gives us our mass. But they tossed in a density. My guess is you'll probably get 1 point for the mass. So with the density, I'm going to write this down. 17.6 grams of ethanol, F, times, now my density is, I'm going to cancel out grams, 0.79 grams per 1 ml. All right, so I'm going to need a few more mLs on this. I've got my previous answer in there. Sometimes it's a good idea not to erasing what you've done. I'm just going to divide right now by the 0.79. Yeah, 0.79, and it's going to give me mLs, 22. And round it off. You could have 23, but I'm keeping it to 2 sig digs because of the density. That is my answer. Now let me double check things. I've got my moles of CO2, change the moles of ethanol. I've got a formula weight here. 24 plus 6, 46 grams per mole, and we're set. This is probably another couple more points. We're moving along. We're at D already. Good grief. Determine the amount of heat in kilojoules that was released in the combustion reaction. Oh, let's go back to our original page here. But I see right here that 1 ethanol ends up releasing negative 1270 kilojoules per mole of reaction. That is, when it says per mole of reaction, it means for all the moles that you see here. 3 moles of oxygen will give you this much heat when it burns. So let me just write that down. 1270 kilojoules. And then that is per 1 mole. And we figured out earlier 0.767 moles. Oh no, that wasn't the methanol. We ended up having, that was for the carbon dioxide. So I figured out my moles of ethanol here would be half that. Or I could have, just divide this by 2, which is going to be 0.767
0.383 moles of ethanol. And I'm going to take my calculator, 0.383 times 1270. Voila. Units are really important when you in thermo, because sometimes you worry about joules, sometimes you worry about kilojoules. So we're going to say kilojoules. And that was, let me double check, the moles of ethanol would be half this, 0.383. We're fine with 486 kilojoules energy being produced by this. Now, this was our 22 mLs burning and produced this much heat. And that's a reasonable amount. Now, the combustion reaction occurred in a closed room containing air. Okay, at 21.7 degrees. Assume that the heat produced by this reaction was absorbed by the air. That's Q, yes. And they give us a specific heat on top of it all. Determine the final temperature of air of the room in combustion. I hope you don't have to go to the equation sheet to remember this equation. Q equals mc times delta T. We've got our Q, 486, but got to be careful with units because our specific heat is in joules. So this is going to be times 10 to the 3 joules equals our mass. We're heating up a heck of a lot of air, but it's a room full of air. 0.556 times 10 to the 4 grams. Yeah, that's how many grams of air we had in there, times its specific heat, which was pretty much 1. Probably not even worth writing down the 0.005 joules per gram degree Celsius. Okay, grams cancel. We're going to get our joules. Calculator time to find our delta T. Oops, I've used up 15 minutes. Time for my calculator, and I got 5 minutes left, so I better get rolling. Calculator, I get this screen rolling. My 46 times 1,000. Get that there right away. And then divide by 5.56 times 10 to the, where's my times 10 to button? Hope you know how to use your scientific note. Yeah, you better by now. And then divide it by 1 point. It's hardly worth the 0.005, but hey, it's there. And I get a delta T of 8.7 degrees. I could get 3 sig digs out of this, but 8.7 degrees Celsius. The original temperature was 21.7. So 21.7 degrees Celsius plus 8.7. Anyway, we're good in terms of columns. I mean, a 100th of a degree would mean nothing. So in terms of significant figures, okay, 30.4. Let me just double check that. It's probably worth doing. Sometimes you get sort of panicky on an FRQ and you make some mistakes in addition, and we've got my calculator here, 30.04 degrees Celsius. Okay, I'll put this in. I've got it circled. They'll see my answer, and time to go on to the next question. We're at E, near the end, and we've got a few minutes left. Let's see. F. The boiling points of ethanol and dimethyl ether are provided in the table. Okay, boiling point. Ethanol 78, dimethyl a lot lower. Okay, boiling points we know are all about intermolecular attractions. So dimethyl's got less intermolecular attractions. Oh, here we go. Identify the intermolecular force that is most responsible for the difference in boiling point. In terms of force, explain why the boiling point of ethanol is higher than that of dimethyl ether. Okay, we look here. We've got an ether. It's got a dipole. So ether has dipole. Notice the hydrogens aren't attached to the oxygen. Dipole. And ethanol, as all of our alcohols, has an OH. Ethanol ends up having OH, hydrogen, bonding, H bonding, has greater IMFs. Let's see. In terms of force, explain why the boiling point of ethanol is higher than that of dimethyl ether. Your ethanol has hydrogen bonding versus, I mentioned the ether, which has dipole-dipole. You got to mention both items to get the full credit. So, and I said that the hydrogen bonding has greater IMFs. That's it. Okay, now on to the last part. I still got some time. Great. One method of producing ethanol by the reaction of ethane and water is presented below. Okay, here we're making ethanol. Exothermic reaction. A chemist wants to run a reaction and maximize the amount of ethanol. Identify 2 ways a chemist could change the reaction. Okay, that's Le Chavalier stuff. Other than adding or removing any chemical species, so that makes it a little bit tougher, to favor the formation of more product. Okay, if we can't add anything, we've got 2 things. We've got temperature and we've got pressure. So let's see. Temperature. This is an exothermic reaction. So we have our reactants. We've got C2H4 plus 1H2O. We want this to go forward, and because we want to make more alcohol, we're making one of our alcohols, and heat is in effect a product. If we decrease heat, shifts the reaction forward. This is all you really need. That's one thing. Okay? Decrease the heat. Lower temperature. I'll put that down. Lower temp. We've got 2 moles of gas. 2 moles of gas. Here we have 1 mole of gas. Increasing pressure by decreasing volume will shift the reaction forward because fewer moles of gas. Because of fewer moles of gas. Single line crosses things out in product. Voila, we finished, and my timer just finished. Oh, beautiful. Did it in 20 minutes. That was the last part of 1. So we're all set. Great. Okay.
We got everything answered within the time limit. So we're ready to go on to the next FRQ.